Most people here, so we're gonna get started. So I posted all the homeworks so that you get a better picture of what you're gonna expect for the semester. So as you already know from last week, homework on different points for each chapter, right? So there's 7 homeworks, and in each homework you see there's a review of examples. There's in-text like exercises. Those you don't have to submit for credit. Only the end of chapter problems you need to submit. So roughly the problems each chapter, roughly for 1 to 6, and then 7, I think they're 20, because 7 is more important. So try to do all of them and submit that for credit. Don't submit the example and the in-text exercises because those don't count. Okay, so don't submit those. When you submit your homework, like collectively mark each problem. Don't just bunch them together, and for the TA hard to look for which problem is for which question. I think the best way is to do 1 on each page, like 1, 2, 3, 4, and then just scan or capture them and submit it as one PDF file. So that will be easier. For the homeworks, of course, you can do it ahead of time. There's nothing wrong with that. But of course, you can always wait until we have lecture already, and then you can do those homeworks. It may be easier to do it after we cover in lectures. I know some students are ahead of the schedule, so you can feel free to do it ahead of time. Chapter 3 and chapter 1 will not be tested in the middle term and final exams, so they're only homeworks. So then you might say, okay, why do I, would I have to learn it if you don't test it? Well, those are like chapter 1 is really fundamental for you to move on. If you don't understand nodal analysis at this point, it's probably better for you to stop taking this class because you need to go back to learn nodal analysis. Otherwise, I mean, there's no way you can move on with the class without understanding how nodal analysis works, right? Chapter 3 just a little bit on semiconductor physics, so you understand a little bit of what's going on with, when people talk about semiconductors, what does it mean, what exactly it is. So we understand a little bit of the background, which is good. So we can go ahead. Today we're going to start chapter 2. Chapter 2 is the easiest chapter in this whole class. So there are a couple of things you make sure you remember. And once you remember that, you will be able to solve any problem, any simple problem or any complex problem very easily. So I will start with it, and then I will summarize it. So we're probably going to spend today and next week to cover this whole chapter. Thursday, we have a TA coming here to do the SPICE simulations. If you think you're really good at SPICEs, it's probably an opportunity for you to review and also understanding that he's going to demo like diodes, BJTs. Those we have not covered yet, but those are going to be really helpful. Looking at how he does it. Yeah, so this is very helpful. And probably today, either today or tomorrow, I will post the 2 projects. So once the project is posted, there's a deadline. So you can, once like Thursday, you have the simulation workshop, you can go ahead and do those problems. Now, of course, some of the content we have not covered, so it might be more difficult to do it at this time. You can always wait until we cover it in classes, and then you do it. And the clear steps to follow how to write your report and how to get credit. As I mentioned in the very first lecture, homeworks, projects, 20 points total is something I give away. You should try to get most of it. If not 20, you should get 18. Now, if not 18, you probably should get 16. If you get less than 16, you're not doing your job. Okay, so I mean, we got to work together. Okay, so let's move on with the class today. So today we talk about op-amps. Op-amps also stands for operational amplifiers. So what they do, they amplify signals. So typically we talk about small signals. Millivolts come in, sometimes of course could be going to volts, but most of the time we'll talk about millivolts. After the amplification, you get a larger, like hundreds of millivolts, sometimes of volts. So the amplification can be quite big. So inside the op-amp, we mostly in this chapter, we study idea op-amps. Now I'll let you know what idea means, okay? There are a few sections towards the end of the chapter talk about imperfections and ideas. We don't cover those. Those are covered a little bit in E430. Now, of course, you have more interest, you can always go learn that now, but it's not going to be tested in the final exams. And then within the idea op-amps, we talk three kinds of amplifiers. So there's inverting. Inverting by the name means reverse, right? By the means negative. And the non-inverting means the positive. Right? And then there's a difference amplifier, sometimes called differential amplifiers, and sometimes called difference. The difference and differential, the meaning of between difference and differential, there's no big differences. But basically, you take the difference between two inputs. But differential sometimes means they don't have a common ground. And difference could mean that I'm taking the difference, but the two actually share the common ground. So that's probably the only difference you can look at. And finally, we're going to cover a little bit of integrators and differentiators. Now, you probably learned this already in 210. If you have a capacitor, you have a, say, current coming in, and the voltage will start to increase, you got it's integrates. And differential means the inductor, right? So if you have an input coming in, let's say you have a voltage coming in, and the output is a differential of the input voltage. So it's a, the differential of the current. So di dt times L gives you voltage, and C times dV over dt gives you the current of a capacitor. So we're going to see how they work in op-amp. I'm probably going to a little bit later on my switch between this and also the blackboard as needed if I want to have more examples. Okay. So this is a symbol of op-amp. Very simple. A triangle, two inputs, one output. The input with the negative terminal, see, number one is called inverting, means it's negative. And the one with the plus sign called non-inverting. I guess the question is why you call it inverting, non-inverting? Why do you call it positive and negative? Well, I guess you will see in the next few slides, the meaning of inverting is very much different from positive and negative, okay? So that's why they call it inverting. So somebody, I think, is very smart. They made the definition at the time. So, and within this op-amp, you have a few very important characteristics you got to remember. And this is what we call the ideal op-amps, okay? So the input resistance is infinity. So when input resistance is infinity, what do you think what happens if you apply voltage at the two terminal? Would you see a current? No, because if you apply voltage and the input, the resistance is infinity, therefore the current is zero. So means no current going into the terminals. So this is very important. No current going into any of the input terminals, okay? And second point is A is infinity. The gain is infinity. So in the very second bullet, I said VO, the output at 3, is A times V1 minus V2. Okay. Now, coming back to here, if A is infinity, what does it mean? So A is infinity. So for any, let's say you're at output 3, you have some sort of voltage, 2 volts. Give you example. A is infinity. What do you mean? What do you get for V1 minus V2? From mathematics?
So if the voltage across it is 0, then it would be 0? Or
You're pretty close. Right. When you learn mathematics, you remember how you take limits? Like x over sine x. When x approaches 0, what happens? Both 0, and then you get 1, right? So that's how it works here. When you get infinity times something approaches 0, if they are in the same order, you actually get a constant. So which means if A is infinity, the voltage between 1 and 2 has to be 0 or close to 0. It's a very small number, close to 0, 0. So in the future, we just call it 0. 0 means the voltage at V1 and V2 have to be the same if you have a fixed output. Now you might say, okay, well, earlier you just said that if I have V3 raised 2 volts, what happens there? Or if I have A times V1 over V2, if I do apply voltage at V1 and V2, there is a difference. What happens? Well, because the gain is infinity, you have some voltage, fixed value. Yeah, ideally, a fixed value times infinity will give you infinity. But the op-amp cannot give you infinity output voltage because the power supply is limited. So if a 5 volts power supply, it gives you 5 volts. That's the maximum you can get. So that's called saturated. Okay, so that's what happens here. And then finally, the output resistance is 0. 0 means output resistance 0. Remember we take output resistance from last week? Yeah. So which means whatever voltage at V3 is applied to the load, there's no current going in. I mean, no voltage drop inside the op-amp. Okay. Now it can be current going in. Okay, it doesn't mean like in the input side. Okay, so this is the difference. At 1 and 2, no current coming in, but 3 current coming either come out or going in. Coming out, called power, like current coming out is supply power. If current going in, it's called sinking. So it absorbs power. So that's what happens to op-amp. So let's summarize it a little bit here, which means if we write down here, so A is approaching infinity, and V minus is V plus. Okay, now this is in circuit. You can certainly apply voltage, but certainly when they are inside the circuit, it's always the same. And I plus equal to I minus equal to always 0. So those are 3 important pictures. Now, of course, later on you can see the R in is infinity and R out is 0. Okay, those are the very important characteristics for this op-amp. If we take the previous, yes, go ahead. A is a gain. Yeah, so A is the gain. You look at this circuit, which means, yeah, it's a parameter op-amp. The gain means whatever input multiplied by gain is your output. So that's the gain. Something coming in, multiply gain gives you output, right? So that's the gain is infinity. Yeah. So to take a little bit further, an op-amp should have a power supply. Sometimes we call VCC or DD or VSS. The E means emitter and C means collector. That's for a BJT. So often we, especially in this chapter, in this class, we omit. So we don't draw 4 and 5. Okay. So therefore, you look at op-amp. Here is how you connect the actual power supply. So negative, say negative goes to 5, and positive goes to 4. So this is, and then of course we connected input at 1 and 2 and output at 3. So for this one, as you can see here clearly, how many terminals, minimum terminals do you have? Do you have to have, for op-amp to work? So there are 5 terminals: a positive power supply, negative power supply, input, 2 inputs, and 1 output. So this is minimum terminals you have. Now, some students did ask last week, so, oh, what happens if I don't have a negative power supply? Well, it is possible to design op-amp without negative power supply, but most of the time, really, you have to consider to have a negative power supply. So 5 terminals minimum for 1 op-amp. And if we want to draw the equivalent circuit, you can always apply a voltage V1, a voltage V2, because there are 2 separate input terminals. Because we said the input resistance 0, I mean infinity, which means from 1 to 2, they are open, infinity, no resistance, open circuit. And output is A times the difference between 1 and 2. So this output voltage, controlled voltage source, and no output resistance is 0. So this is the equivalent circuit of op-amp. And sometimes if you get confused, oh, how does it work? You always refer back to this diagram. So move on. Now get into the most interesting part. Is we connect a voltage at terminal 1 with ground terminal 2. So terminal 1 is called the inverting terminal. We connect to input voltage with a resistance, and that resistance has to be there. Later on, you'll see why. And of course, sometimes the input voltage also has an internal impedance, like RS. In here, we neglect it. We ground terminal 2, the non-inverting terminal, and here's the output. The output right now did not connect to any like load yet. But we did put a resistance between 1 and 3. So I want to bring this idea to test you guys. 3 is output. Terminal 3 is output. Terminal 1 is the input. So we connect the 1 and 2 through something, the resistance. What do you call, if you imagine, what do you call this? A feedback, exactly, a feedback. Because now, because the 3 is your output, now you connect your output back to your input, so your input also sees the output. So that's called a feedback. So op-amp, in ideal op-amp, it is always working in a feedback. Okay, always feedback. There's no exception. For op-amp, ideal op-amp circuits, like particularly when we learn in this class. So now we want to analyze this circuit to find out for a given Vi, what would be the VO. So how do we start? Well, we want you to remember a few things that we mentioned earlier, is that so I minus I plus. So I minus I plus, right? Remember this, 0, right? Infinity input resistance, no current going there. So if no current going there, if we assume there is a current over here, I, and we're going to call this voltage here V1, and we call this voltage over here VO. So if there's no current going into the op-amp, what happens to between I1 and I2? Okay, this is called II. So you probably can tell me right away, is I1 is going to be equal to II, right? You see the current going this way, right? This can also be verified by nodal analysis, right? So we can also do nodal analysis at this V1, which means we have Vi minus V1 over R1 equal to V1 minus VO divided by R2, right? So we apply nodal analysis at node V1. So you see current, the first current is V1 minus Vi minus V1 divided by R1. That's current coming into the node. And the current coming out of the node is V1 minus Vi divided by R2. There's no current going into the minus terminal. So therefore, those two currents are going to be equal to each other. Yes? Vi is here. Yeah, input voltage. Yeah. V1 is the voltage at the terminal 1. Yeah? Clear? Okay. Now the problem, of course, over here is that we have two variables because we want to find VO, but we introduce another variable V1. So we have a little bit of trouble here to find VO, but we can always write VO as a function of VI and V1. But the problem is that we don't know V1 will be in trouble. So now we need to go back to the concept we talk about is the gain is infinity. So which means we do know VO equal to A, which let's say A is O here, but A is, of course, infinity times V2 minus V1. Now, I just want to make sure you guys understand here. I write V2 minus V1, not V1 minus V2, because V2 is positive, right? V1 is negative. So the output is, the input is positive input minus negative input applied by the gain gives output. Now, since this A is infinity, and we know that VO has to be some sort of value. Now, because you say, how do you know? Well, eventually you will know. But here, let's assume V1 has a fixed value. But A is infinity, which means V2 and minus V1 has to be 0. Okay, that's important. Since A approach infinity, V1 minus V2 minus V1 equal to 0, which means V2 minus equal to minus V2 must be equal to V1. But we know that V2 is 0. See, V2 here. V2 is grounded. Therefore, V1 equal to 0. So now we can plug in this back to here. So V1 is 0. I can do it over this way. Let's see. Because V1 is 0, we directly have Vi divided by R1. I'm taking this equation here. Equal to V1 is 0, right? So equal to minus VO over R2. So multiply by R2 on both sides and move the negative sign over the other side. We got R2, R1 times VI. Or further, we have VO over VI, which is the gain. Let's call it equal to minus R2, R1. So we find VO here is simply V1 divided by R1 times R2, and there's a negative sign. So now by this time, you probably understand why it's called inverting, because when you have an input connected at that inverting terminal, your output is actually negative. Now, of course, that negative, remember, you have to have a negative power supply. If you don't have a negative power supply, your output will be 0 because there's no way you can supply the negative. So this is a very important equation. So VO equal to R2 over R1 times VI. So this is called our inverting amplifier with a feedback, ideal op amp. I think probably the most important part is just to figure out. Here has a little bit of detailed step-by-step analysis saying, giving some other concepts. Because the current going into the terminal is 0, because the gain infinity, so inverting and non-inverting terminal voltage is always the same. So regardless of what happens, you always remember V minus and V plus or something like V1, V2, they're always the same. So therefore, here it gives you a circuit. So if this is grounded and this is a virtual ground, they call it virtual ground because it is not actually grounded, but the voltage is 0 because the infinity gain, right? And of course the gain is infinity. And now you see here, this V1 minus V2 minus V1 is 0. So A times 0 is infinity. Therefore, they give you some sort of fixed voltage. You cannot calculate from this equation, but you actually have to calculate from the feedback. Right. So we're not going to go too much detail over here, but I want to, yeah, okay. See. So what we're going to do is we're going to go to a more complex problem and to see if we can figure out the steps to solve the problem. Once you figure out the step to solve the problem, and once you understand, you remember how to do node analysis, all the ideal op-amp circuits becomes very easy. And I said very easy, I mean it. Okay, it's really very easy. Okay, so in this circuit, we have a very similar circuit to the previous one at the input. So our non-inverting terminal is grounded. Our input here, it draws VI, didn't draw the actual voltage sign, but that's fine. So you know that this is like a voltage input, and there's input resistance R1, and that's output VO. In the middle, instead of having one resistor, it got actually R2, R3, and R4 with sort of more complex circuit. It does make it more complex, but we need to remember a number of things here. So I think probably the most important two things, if you remember, you will be able to do the problem very easily. Number one is V minus equal to V plus. And sometimes they call this V1 and V2, okay? So, you know, whatever circuit marked, you just remember, non-inverting terminal and inverting terminal, the voltage are going to be the same. Number two, I minus. And of course, these two other conclusions and also the concepts that you need to remember, to do a problem. These are derived from the properties of op-amps. Like the first one property, how did we derive it? Because the gain is infinity, right? So that's how we derived the first one. How did we derive the second one? Because the input resistance is infinity. So basically, those two are from I actually just erased it. Let's see. So V plus equal to V minus equal to, this is because of A equal to infinity. And number two is I minus equal to I plus equal to 0. And this is because our input and resistance is infinity. Yeah.
I think you moved on to.
Huh? What is it?
You moved on to a current amplifier instead of the 2.2, or did you just move off?
Oh. Okay. Well, yeah. You're right. Okay. But okay, good. Thank you. Well, this equation still apply. Okay. So yeah. Okay. Good. Well, I didn't know. The two circuits look similar, right? Look very similar. So by doing this, in this circuit, how many nodes do you have now? How many nodes? You look at. So most likely, people might say, well, you have like a node at the non-inverting input, right? That's a 3 terminals going to something. That's typically called a node. And another node is at X, right? That's a 3 terminals connect together. That's a node. At the output, you can connect a node. You can call it a node, but here really it's not a node because there's nothing connected. What I'm saying is here. You see, there's nothing connected here. If there's something connected here, that will be considered a node. But this is nothing connected here, so this is basically lying together. So this is actually, you see a dot here, but it's not a node. So ideally, this has two nodes. But we can further simplify this to one node. Why? Because there's no current into here. If there's no current here, you see these two are going to be connected in one branch. But of course, the node here is important because we want to solve the circuit because V plus and V minus are going to be the same. And V minus is 0, so V plus is going to be 0. Okay, so if V plus 0, we don't even have to do the nodal analysis. We can immediately find what is the current through R1. Right? Can you find? So Vi is 0. That's what we find out. So I is going to be Vi over R1. So we find it this one, right? We find II easily because the non-inverting terminal, the inverting terminal voltage is the same as the non-inverting terminal, which is 0. And we use Vi minus 0 divided by the resistance on the branch, we get the current. So if no current, again, no current going into the inverting terminal, all the current I1 will go where? It's going to go up. Therefore, you will find I2 equal to how much? Go to II, okay? So I2 is equal to II, right? So now you do have a problem is that we cannot find I3 and I4 because there's node Vx over there. But fortunately, we can write the nodal analysis on Vx, right? So if we know on Vx, we can write I2 plus I3, or the current coming in, equal to I4. Now I2 equal to, we already find I2, right? And I3 is I3 equal to Vx minus R3. And I4 equal to Vx minus VO divided by R4. You guys follow? Yeah.
Like before, how do you know which one to subtract first? Is it always?
Well, you need to mark the direction of current.
Oh yeah.
You see here, we mark R2 and R3 going in and R4 going out. So actually you're right. So I2 plus I3 equal to I4, that's correct. But what I did, I3 is actually, you're right, I actually did it wrong. I3 should be minus. Yeah.
0 minus.
Yeah, 0 minus, 0 minus Vx, right.
I4 correct? Like that.
I4 is correct. I4 is Vx minus VO, that's correct. Yeah. Okay, so this is so equal to minus Vx or R4. So, well, the point is that we now introduced Vx. We want to find VO, but we introduced Vx. So we have trouble. But fortunately, we know Vx is going to be, let's do this. So Vx 0 minus Vx divided by R2 equal to how much? Say 0 is here. 0 is that that the inverting terminal is 0. Minus Vx divided by R2 is the current going into R2. And that current is equal to I1, II, right? So that's is I2, but it's also equal to II, which is equal to II, we just calculated Vi over R1. So right away, you can get Vx. So Vx will be, which minus Vx here is going to be minus R2 over R1 times Vi. So you find Vx. Okay, now you can plug in Vx over to this equation here, and this going to this equation here, and we can find actually plugging this to this equation here, right? I3. So I3 now becomes minus Vx over R4. When we plug Vx in, so it's going to be plus plus, so go R2, R1, R2 plus R1, R4 times Vi. So we got R3. Now we have I2. We can easily find I4. So I4 is going to be I2 plus I3. So I2 we find is Vi over R1 plus I3 is R2 over R1, R4, Vi. And then therefore you can have you can have I4. Now finally, we know that Vx minus Vo divided by R4 gives you I4, right? So we know that now Vo is going to be Vo is going to be I4 times R4 minus Vx, right? So we just times R4 on both sides, and we move Rx on that side, Vx on that side. So now we multiply both sides by minus sign. We got Vx minus I4 times R4. So of course, Vx we already find over here, plugging here, and I4 we plug here. We can find the output voltage. Yeah.
Shouldn't I3 be minus Vx over R3?
I3, yeah, I3 is minus Vx over R4. R3, yeah, you're right. Sorry, yeah. Okay, sorry, thank you. Yeah. Yeah. So the R3 copy here, you should be R3, okay, good. So now you can find the actual value. So we're not going to spend time on writing the final equation. Yes.
Does that change all the values you have at the bottom there?
No, it doesn't.
Well, you have I3 Vx.
Yeah. I3. I3, yeah, so it's R3. Okay. Yeah, you're right. Okay, thank you for pointing that out. Yes. R3 over R1 times R2
That should be R3.
should be R3 too. Yeah, should be R3 too. Yeah, 1 over R3. R2 over R1 times R2 over R1 times 1 over R3 times Vi. Okay. Those examples are in the book. So just what I wanted really just to get the actual steps. So this is the same example, but in fact, we change the voltage source into a current source. So that will make it a little bit easier. The way that it works here is that because this is voltage here is 0, so voltage here is 0, right? So that's another thing, same thing. And then we have current going here because there's no current coming in here. So therefore, all the current will go up. So you can see our I2 is equal to I1 over here. And because this is 0, you have I2 going there. So we can easily calculate voltage at, you can call it Vx here. So because this is 0, 0 minus Vx divided by R2 equal to I1, equal to I2, right? So by I2 equal to I1. So therefore, we can find Vx equal to, this is going to be minus I1 times R2. See, so here, I think also important to visualize that Vx is negative. Why Vx is negative? Because you have current going that way, and this is 0. So voltage Vx has to be lower than 0 for current to flow, right? So current has to flow from 0 to a lower voltage. So therefore, Vx is negative. Yeah.
With a fire like this, like it's current, how do you kind of extract the current? Like if you put this in an actual circuit, it says like R4 is the output, right? Or something like that? Or...
Oh, no, R4 is not output. This whole thing is a feedback. The output is over here. The output is over here. So in real life, after the amplifier, you would do something like this. You would do something. Okay. So but here, since the voltage at the output, the voltage at the output here has nothing to do this one. Once you find the whole voltage here, you can use the voltage divided by load resistance, you get the current. So because it has nothing to do with output, so typically you see a lot of the analysis don't have output. It just simply have the output node over there. Okay, so moving on, now we find Vx negative II times R2. Then we can use Vx, so Vx divided by, so 0, so now 0 minus Vx divided by R3 equal to I3, right? So now you plug in I3, plug in Vx, you will get minus becomes plus R2 I3 times I1. So I3 equal to I3, because 0 to Vx is negative, so I3 is actually positive. So I3 is also from ground, which is below R3, that's 0, to Vx. Vx is negative, so I3, we find I3 is R2 over R3 times I1. Okay, so you find that. Now, once you find Vx, you can use Vx minus Vo divided by R4 equal to I4. Now, of course, we know that I4 equal to I2 plus I3, right? So because I2, I3 we find already, if we can find I4, plug in. Now you can find Vo equal to, let's just simplify, manipulate that equation, you will find like equal to Vx minus I4 times R4. So Vx is already negative. Vx is already negative, which and then you minus I4 times R4, which means Vo is further negative. So if you have numbers, it will be easier to do. Just find like 1 volt, and you get minus 1, and you get minus 2, maybe something like that. So so ideally, in the future, you will see that this 0, that's the most important part, and then this 0 also. So Vx is negative. Okay. So if we can plug in some actual numbers to make it better to understand. Okay, so if let's say this is 1 amp, this is 1K, so this is 0 volts. So how much voltage do you see here? Minus 1 volt, right? So if R3 is also 1K, how much do you see the current over here? Oh, 1 milliamps, not 1 amp. 1 milliamps. Okay, so that's also 1 milliamps. And I4 will be 2 milliamps. If R4 is also 1K, and how much voltage do you get over here? 2 milliamps. So that will be like from here to here is 2 volts. So from here to here is 1 volt. So Vo is minus 3 volts. You get those numbers, correct? Did I do it right? So make sure sometimes numbers can get confusing. Yeah. So 1 milliamp coming in, 1 milliamp coming in, going to the 1 kilo ohm resistance. So there will be 1 milli times 1K gives you 1 volt. So Vx is minus 1 volt. This is also one case, so 1 milliamp going up. So 1 milli plus 1 milli is 2 milli. So 2 milliamps for R4 times 1K is 2 volts. So from Vx to that is 2 volts. But Vx is already minus 1. So therefore, this is minus 3. So often, like one mistake students make is that, oh, see, that's 2 milliamps times R4 is 1K. So 2 milli times 1K is 2 volts. So therefore, they say this is minus 2 volts. Okay, so that's wrong. And sometimes they forget the minus sign. They say this is plus 2 volts. That's also wrong. And sometimes they forget the minus sign, saying that's 3 volts. That's also wrong. So it can be easily to make a mistake. Yeah.
Sorry, this is a silly question, but like, why would you use an amplifier? Why can't you just like add a bunch of current sources instead? Like, why are we doing this? You know?
Why?
Just this is like.
Because our signal strength isn't, this doesn't really make sense when you're talking DC, but once we're talking an alternating or a signal path that changes over time, that doesn't make sense. Or if we're trying to say, for instance, the most common use for amplifiers, like sound.
Yeah.
If you're taking in a sound signal and you want to increase the volume from the original signal, you'll use an amplifier.
Yeah. Amplifier has right. Yeah, that's great explanation. A lot of signals in life are coming very weak, very small. Take a cell phone, for example. You receive this little antenna, you receive some sort of electromagnetic waveforms, generated output, probably in the microvolts. You can't use it. Too small. You cannot hear because it's too small. What do? Use a bunch of amplifiers. You amplify them 1 microvolt to much larger, eventually going to be a few volts. And that a few volts going through like a speaker or something that you can hear. Yeah. So we need to amplify. Now, this amplifier has to be nearly ideal because the amplifier has to have a very large input resistance. Otherwise, you got all the input lost. You can't just take it. And we have to have very small output resistance because you want all the signal that you amplify to be able to use it. You don't want anything to be dropped inside this amplifier. Very useful. Okay, great. Yeah, so this one, I'll probably skip this one because it's the same thing, just going through. But let me going to talk a little bit about the type of input. Now, in the previous example, you see initially there was a voltage input, and then we look at the current input. So which means this amplifiers can take either current input or voltage input, it doesn't matter. As long as you have the circuit configuration configured right. So in this case, we say that we have op-amp, the non-inverting terminal, again, grounded, and inverting terminal is connected through a 10 kilo ohm resistance to the output, and we have input connect to the non-inverting terminal. And then for the input side, so we have this input, a current source with a parallel resistance. Remember, when you have a current source, the internal resistance is always in parallel. When you have a voltage source, the resistance is always in series. That's kind of how this is set up. Now, of course, I think you guys have not even asked, why is that, feedback is on the inverting terminal? Can you connect it the other way around? Like, can you connect the feedback at the positive terminal instead? For example, instead of doing this, can we do this? So this is we have not learned a lot of the circuits yet. We dive right into ID op-amp. Our op-amp is built by certain type of electronics and putting together. They look like idea, but they're really not idea. But if you look at the feedback, what the function of a feedback is tie the output back to the input, right? So if output increases, if input increases, so output let's say if input increase, output increase, that's like a typical open loop amplifier. The more input, the more output. Now, if there's a positive feedback, what happens that if input increases, output increases, and the difference at the input increases, the output is even more. The input increases and output increases and even more. So it goes back, the output eventually goes to saturate. So that's a positive feedback. But for negative feedback, that's exactly different. So probably I think it may be a good idea to explain this down to your feedback. I don't know if you guys have learned this already, but let's say you have some sort of block diagram. Let's do it like this one. We're going to look at some sort of PI later, proportional integrator. Let's say it's your output. Oops. I don't know how to erase this one. Is there an eraser? No. Actually, that's okay. Let's forget about this one. Let's call it V in, VO. So this is a negative feedback. With the PI controller, proportional integral. Actually, by the end of this chapter was introduced a little bit concept about PI. See, what happens with this output is VO equal to KP times epsilon equal to so I just want to take the difference between VI and VO is called error signal. So and then the output is integrator plus a proportional VO. So if at this point you can see what happens if VO and VI is the same. If they are the same, what happens? If they are the same means error is 0. If the error is 0, the first term Kp times omega is 0. But the second term is the integrator. And you guys know what integrator means, right? If omega 0, which means the integrator is, why it becomes constant? Yeah, the integral is 0, but whatever initial value is there, right? So integrator means initial value plus whatever it goes up, right? So initial value, so it's a constant. So if VO and VI is the same, the output becomes a constant. Now, if let's say VO is less than VI, now the error epsilon is larger than 0. So the largest is 0 means Kp times epsilon is positive, and the integrator also increases. So what happens to VO? Increases. So which means if VO is less than VI, your system will make VO increase, and eventually will get to a point VO and VI. No, VO and VI will become the same. The idea is, that once it becomes the same, it stays, right? Okay, so if VO is larger than VI, what happens? The error is negative, which means your VO start to decrease. It's a regulator, right? So eventually it will get to the point this two has to be the same. So this is negative feedback. So negative feedback means if your output increase, the error becomes like a negative, and it will pull it back. If output decreases, it will go like this. A typical example is you guys doing this driving. I think this is the best example. Like when you drive, you always look at the speed of your vehicle, saying, "Oh, what speed too fast?" What do? You slow down. You release the the gas pedal or you press the brake pedal so your vehicle slows down. Once your vehicle goes to the speed you want it, you try to keep your feet like easy, okay? Just not too much, not too little, just keep it, right? So then if you do this cruise control, the system does it for you, so you don't have to press the brake or the gas pedals. Actually, the cruise control looking at your vehicle speed and look at your setup. And if your speed is too fast, it will reduce gas, or it will apply brake. If your speed is too slow, it will accelerate gas. Right. So that's exactly a control. But if you have a positive feedback, you're going to have trouble. So your output is going to be k times epsilon plus integrator of times. Okay, so ideally, if your VO and VI, like, well, this is probably not the best way, but that's okay. I mean, so what you're doing, you're taking VO and VI, you add them. So if you add them, so your epsilon becomes like bigger, so this becomes bigger, right? Every time your VO becomes bigger, this is even bigger, and then you go all the way, eventually you saturate, right? So if VO is negative and VI is positive, and eventually you'll go to the other direction, basically. So this is, so positive feedback doesn't really work. So going back to our op-amp, so our input can be at both sides. By the way, you will see, like, probably by, so you will see by next lecture that we can have input on both terminals, but the feedback has to be always at the negative input or inverting terminal. Yeah, go ahead.
When the feedback is to reach saturation faster, I was still a little unclear why, what the point of feedback.
The feedback is so when we put, so we want it in the negative terminal, so it subtracts us, gets us the
Yeah.
appropriate.
Right, but when it's just a resistance.
The feedback is try to maintain a certain output, because the gain is so big. Like the gain is like, say, infinity right now, but let's say it's not infinity, not even. Let's say it's 10,000. So if you have 1 millivolt input, what happens to your output? It's like 10 volts. You have a power supply of 5 volts. You're already saturated. You only can get 5, right? So that's kind of unstable. So feedback, is a lot of feedback we'll be talking about in E430. There's a whole chapter about feedback control. It is going to be, you need feedback because you want to regulate, you're right, to regulate your output to your input with a relative, like, wide bandwidth, less sensitivity, things like that. For example, let's say your input is 1 millivolt. Let's say your actually amplifier works still in a linear range. But if your input changes 20%, your output changes 20%. So translated to a phone, which means your input signal comes in like 1 millivolts, you can hear clearly, but if it changes 20%, you cannot hear anymore because it's like too low. But with feedback control, if your input changes 20%, your output only changes maybe 1%. So it stables your output. Yeah, very useful for feedback. Okay, so much about this feedback. Now let's go back to the circuit. So if we have input with, so this will not do. So let's say we have, you guys are going to see a lot of this circuit. So if you have this circuit, we already have like a simple, this is the simplest op-amp circuit you can have. Now, remember, we're going to do it again because we're going to do this many, many times so that you're going to remember how to do it. So we minus equal to we plus equal to 0 because we plus is grounded, so we plus 0, but we minus has to be the same as we plus, so we minus we plus 0. So therefore, we can have so II equal to Vi minus V minus divided by R1 equal to Vi minus R1. Okay, and then our I2, so I2 is going to be 0 minus VO divided by R2. And so VO, and this equal to I2. So this a couple of things like you guys already know. Want to go over this again. Positive terminal grounded, negative terminal voltage, same as positive terminal. So this is 0 and this is 0. This voltage here, minus 0 divided by resistance, we get current II. Because no current coming here, so all II goes to here. So voltage 0 minus 0 divided by R2 gives you current in this branch. But this current branch is same as this current branch. So that's how we did it. The 0, we got I1, which is Vi divided by R1 equal to I2. And then 0 minus VO divided by R2 equal to I2. So therefore, your VO equal to minus I2 times R2, right? And then I2 equal to R1, Vi over R1. So therefore, we can find VO equal to minus R2 over R1 times Vi. So very simple output, which is R2 over R1 times Vi. Okay, so this is with a voltage input. Now, this example says that if you have a current input, what happens? If you have current input, well, the current 0.5 milliamp is connected to the input. So what are we going to do? We're now going back to this part. Let me circle this so that we don't get confused. So we're going to connect this one with current source. So that's called, oh my gosh. So 0.5 milliamp. Okay, just you guys know this 10K. 0.5 milliamp. So for this circuit, now basically, you can employ the same idea is that the voltage at the negative, positive terminal 0, so therefore voltage at the negative terminal also 0. The current comes in to that node. The problem is that when the current coming in, there will be current going through the 10K to ground. And then there'll be current going from that point ground to that way. So all you need to do is to find out, is there any current going through this 10K? Now we know that the current over here is 0. So this is 0 volts, 0 amps. So this current coming in here. So what happens to that 0.5 milliamps coming to that way? Would it be equal split? Let's all think about it. What happens to that? Did I just say the voltage at the node? What is the voltage at the negative terminal? 0. So if that voltage at the inverting terminal 0, what would be the current through that bottom 10K resistance? how much is voltage across that 10K resistance at the bottom? 0, because there's ground here, there's ground there. So there's no current. So if there's no current, right, so all the 0.5 milliamps will go where? The top 10K. So therefore, so there's 0 amps over here. So 0, oh, gee. What happened? Where'd it go? Oh, where is it? Oh, here. So 10K, 0.5 milliamps all going here. Now, because they are not going to write it, you guys already remember, understand why, because the voltage across the bottom 10K is 0, therefore there will be no current. So how much VO we get here? So there's a 0.5 amp coming in times 10K, that give you 5 volts. However, the 5 volts is going from 0 to current can only go from high voltage to a low voltage. So if the coming out node is 0, the output will be negative 5 volts, right?
We also by doing revenue equivalent, because we have a current source parallel with a resistor, and then we could just make it a voltage source with those.
You can do that too. Yeah, of course. Yes, you can do that. Okay. So do you guys catch the idea? Let me see if we have more examples. Oh, interesting, because you guys keep asking what happens at the output. So here we connect output resistance. Now, once you connect output resistance, you'll be able just one more step is to find the output current at the load resistance. That load resistance, regardless how big that is, it has nothing to do with the output voltage. The reason is that you see that node is determined by how much current coming this way. So we're going to do this example anyway. Let's say you have 2 volts. So when you guys do this, you can do the same thing. Just simply mark the voltage, 0 voltage over here, right? So therefore, there's a 0 voltage at the inverting terminal, and there's 0 amps coming in here, 0 amps coming in here. So those are important characteristics. So therefore, we can find I1. You guys can find I1. I1 is how much? Let's do it together. How much is I1? Write the equation. I1 is the current across that 1K resistance. 2 volts. Right? Right? So the non-inverting terminal, the inverting terminal is 0, and the other end is 5, so 5 minus 0. 2 volts minus 0 divided by 1K is 2 milliamps. So how much is I2? Because the current going into the inverting terminal is 0, therefore I2 equal to I1, 2 milliamps. And how much is VO? Well, if you cannot write VO right away, you can always do that loop equation. Okay, so inverting terminal 0 volts minus VO divided by 5K give you I2, right? So that's 2 milliamps. So therefore, your VO equal to multiply 5K on both sides and move the negative sign. So it gives you minus 5K times I2. 5K, I2 is 2 milliamps. So that gives you minus 10 volts. So you can see here that the VO has nothing to do with that RL. So let's call it R. Okay. So how much is IL? Can you calculate IL? Will be the 10 volts minus divided by the 1K. However, the 10 volts minus sign, right? So which means it's going to be like minus 10 volts, then minus 0 ground divided by RL, so it's minus 10 divided by 1K. It's going to be 10 milliamps. Negative 10 milliamps. Okay. So one more step. We want to find IO. How much is IO? IO equal to IL minus I2, correct? Right. So you guys have trouble writing it? You can always write a node equation on that node. You know you have I2 coming in, IO coming in, and IO coming out, right? So you can write I2 plus IO equal to IL, right? So, and then doing that, you have IO equal to IL minus I2. So IL is minus 10 milliamps, minus I2 is 2 milliamps. So therefore you have IO equal to minus 12. Okay, that's, I just can't correct it. I understand, right? Yeah.
So if you know the output, like voltage and current, is there some like resistance that you can calculate that is meaningful in any way?
That resistance is,
Well, we don't know if our voltage output is a resistor or
Yeah.
or like some passive load or
Yeah.
inductive load.
the output resistance, I mean, not the output, the load resistance has nothing to do with the voltage, but the current definitely is defined by the resistance. So if we increase to 10K, right away you see your load resistance becomes 1 milliamp, right? Instead of 10 milliamps. So what I just wanted to emphasize here is that if you see the IO is coming out of this op amp, which means this op amp is supplying a current, in this case 12 milliamps. 12 milliamps is supplied by the
It's not
op amp. Yeah,
It's supplying a negative current.
it's supplying a negative current, right? You're right. It's like a sinking. So that's we call it's actually absorbing power into that op amp. So our op amp can either current come out or current come in. Now in the pre-example, if we change the resistance to 1K, what happens? Right? If RL is 1K instead of 10K. So if, like this example, if RL is 1K, which means that IL becomes minus 10, no, 10K, sorry. So minus 10 divided by 10K gives you 1 milliamp, right? So now IO is how much you see? It's IL minus I2, it's 1 milliamp. Minus 2 milliamps. Okay, well, it's still negative, minus 3 milliamps. There's no way you can get a negative because output is negative voltage, so current always going there. But in the next week lectures, we're going to find out that actually sometimes the op amp can also supply current. Sometimes it can sink current. But in either case, the op amp can do a lot of work for you. Now, what I wanted just to get you a head start for next week is that in this case, output is always negative. With output negative, we have two problems. One is that we always need a negative power supply. If we don't have a negative power, sometimes a negative power supply can be a headache because it's hard to create a negative power supply. And secondly, a negative power supply, a negative output is not very easy to use. So in a lot of occasions, we want the output to be positive instead of negative. So how can you make the output positive? That's kind of what we're going to talk next week. Go ahead.
You already mentioned about plugging amps itself. We just put in another negative amplifier, another negative amplifier.
Yeah, you can do that. Yeah, inverting, yeah, you'll become, you're very smart. But we actually can do a single op amp to become let me see what I have. More examples. Yeah, actually, this is what we're going to talk about next week is No inverting. Well, let's do this next week, actually, because we're gonna spend a lot of examples to go through how to calculate. Yeah. Oh, yeah, Thursday is a spice lecture. You're right. Okay. Remember doing the prerequisite. Okay. If you guys have not done it, remember doing it. Okay. That's a bonus point you need to have.